So, yes, I have a plane, a flat surface. How do I define the plane? How do I describe all the points in the plane and none of the points that are not on that plane?
With a lot of points.
It is a lot of points, but I can't just give you a lot of points because there's infinitely many of them. We would be here literally forever.
With a bunch of equations that make up points.
Sure, what kind of equation am I going to use?
Depends on the shape of it.
It does, doesn't it? Assuming it actually goes infinitely far in all directions. It goes everywhere. It's a big flat surface. It's just a piece of it. How do I define that plane? Let me ask you a related question. Suppose I have a line in 3D space. How do I define that line? How do I define that specific line?
I, J's and K's. What do you mean?
How do we define a line?
Cartesian equation. Is that what you're pointing at?
Yeah. Look at the vector equation, right? What is this based on?
Oh, you got the position and then the direction.
The position of what? You've got to be
The
very specific, but you always just make these general statements. The position of...
line.
Yeah, how do I define that?
With a vector.
Which vector? I need two
The
vectors.
position vector.
Why? Which one? Okay, let other people have a go. What do I need to define the line? You can answer this, Julia. You can. Any of you? Ray, what do I need to define this line? What's A and what's D? Anybody before I give Ben another go? See, you keep telling me, Ray, and you think you are ready to move on, but you don't know this stuff well enough.
I know
yet.
it. I'm getting up to it.
You clearly don't know it.
I'll know it in like 3 days. If you ask me on Monday, I'll tell you everything.
I'm asking you today.
I don't know it today.
And that's my point. Ben, have another go.
A point on the line.
Some point on the line, yeah,
And then a direction.
expressed as,
A vector.
okay, so then I go to that point and then I go along that line somewhere, right? That's how I define the line. Can you think of a way I can define a plane?
Just like that, but long. Like wide.
How do I use a vector to describe something wide?
From the origin to the plane.
We're definitely going to be doing that. We're definitely going to pick some point that I know is on my plane and get
And then
that
there'd
vector.
be a perpendicular one, wouldn't
And that
there?
is point A, and this vector is little a in that formula at the bottom of the screen.
And then what he said. To get the angle.
And then would there be some perpendicular vector as well to show the other direction of the plane?
Why a perpendicular vector?
Because that's the plane. But
Oh, you're saying, and have two vectors on the plane. That would be one way I could do it. I could have this vector and that vector on the plane at right angles. That would happily define my plane. However, that requires three vectors and I can do it with two. Here's the thing. Suppose I have, how do I demonstrate this? Suppose I have two vectors on my plane. We have just recently learnt a way to talk about the plane containing those two vectors with a single other vector. What's my single other vector that takes in information from both of those? It is just above that top point.
cross product
What does the cross product tell me?
tells you the perpendicular, the normal
To what?
to the two vectors.
Which means it's the normal to the plane that contains those two vectors.
Oh, so that would be your third vector.
So all I need to define this plane is a point that's on it and a single vector. Oh, now what too many pens in my hand. A point A on the plane, which I can leave it there, and then a single vector that is at right angles to the plane. There's now too many other arrows on this diagram, it's going to get confusing. Oh, no, I need that one. Too many arrows left. It just got confusing. So what I give you actually is a point on the plane and a normal vector. This vector, again, is at right angles to the plane I care about, whatever that is. That vector is always at right angles.
Is it perpendicular to like the line that A is on, or does that have
No.
anything to do with A?
No, A just tells me, how do I do this? Okay, let's use this. Here is my plane. If I use the normal vector to define the direction of the plane, any of these planes would satisfy that. So I need a point on the plane to tell me exactly which of those I want. A normal vector and a point. How am I going to use my normal vector and my point to define the plane? Well, I'll make that dot look nice. There we go. This vector is normal to every vector in the plane. So if I get a vector in the plane and I do what with this one, how do I state or how do I test whether the two vectors are perpendicular? Are normal.
Equals 0.
Dot product.
Dot product equals 0. So some vector in this plane, suppose I have another point R over here. My pen is not like me today. Suppose I have my point R over here. This vector, dot product with the normal vector, is always going to give me 0, no matter where this point R is. So that's to say R minus A dot my normal vector is 0. This is a vector that's on the plane. To some other point on the plane, from this one I know is on there, that's a vector within the plane. If I take the dot product with my normal vector, I'm going to get 0.
Sorry, what's normal again?
Normal means perpendicular.
Okay.
Normal, perpendicular, orthogonal. Ryan, can you think of any other words they might need to know that means at right angles too?
At right angle?
I'm writing it up. Perpendicular. They're the ones I can think of offhand. These all mean the same thing and you need to recognise all of them.
Okay.
Because any question you come across anywhere might use those words.
Okay.
They all mean the same thing. So this normal vector, dot product with anything on the plane is 0. That's not quite the way it's written now. I'm going to move it up so you can see it a bit better. Oh, I didn't say make it bigger. I said move it up. Thank you. But if I extend this, R dot N minus A dot N, and then R dot N equals A dot N, that's the way it's written up there. But that's where it comes from. This is true because my vector on the plane dotted with the normal has to be 0. This is the vector equation of a plane. To define it, I just need a normal and a point. And that defines my plane. I have my line. There's not enough facts in this book, which is why I've got another one for you. I'm just going to make my own up. I'm going to leave a little bit of space here because I'm going to show you how we get the Cartesian equation. Maybe I should ask you, do you want me to get you to the Cartesian equation first or show you an example of this first?
Show an example of that.
Example of this? Okay, so I'm going to leave a bit of space. I'm going to go, for example, the plane that is normal, orthogonal, perpendicular to N, which is, let's go, 3i minus 2j plus 2k and contains the point A, let's go -1, 2, I don't like using lots of numbers there. To write the vector equation, I just go r dot 3i hat minus 2j hat plus 2k hat equals, this one I can do. It's a dot product of the position vector with my normal, a dot n, right, a dot n. So it is -3 minus 4 plus 8, which is r dot messy twos equals 1. That's my vector equation of the plane. If I replace r with xi, yj, zk, oh, hang on, I better use what the syllabus does. Oh, yes, okay. And A is the point A, B, C. Then what's going to happen?
A and X, B and Y.
AX plus BY plus CZ equals this one is going to be some constant. I don't know what the normal is, but it's going to be a normal and a point. It's going to be some constant. If I call that -d, we'll get the form that has, which means AX plus BY plus CZ equals D.
Why -d?
To make it match theirs.
Oh.
I would normally just go equals D, but the syllabus specifically puts the D on this, specifically puts the D on that side, so I just wanted to make it work the way the syllabus does it. And that is Cartesian equation of our plane. Essentially, this constant in the formula tells me which of those planes it is. That constant tells me where my actual plane sits.
But won't they just solve into a numerical value?
So let's try this. Yeah, this will be a number, yes, correct. It's a number.
How does that represent the plane then?
Because if I don't know what this is, I have an infinite number of points I can choose. This one says only the ones that make this equal to 0.
Okay.
This number comes from, as you're about to see, this, right? A dot n. So in this case, that's my vector equation. Should I label that? The vector equation. If I want the Cartesian, just replace this with x, y, z dot 3i minus 2j plus 2k 3x minus 2y plus 2z minus 1 equals 0. And that's the Cartesian equation of my plane. And this number tells me It's linked to the normal and that point. So this number tells me which of those many planes is the one I'm talking about. It's that one. It's normal to which vector? 3 minus 2, 2. And when I add the points up like this, that's the number I need to make it 0.